Okay, so we've talked about primitive and constructed types for 39 minutes. All right, and now we're moving on. So this is Computer Science 305 Programming Languages. Today we're talking about types. Specifically, we're going to look at the uses for types. So the first thing we have is type annotations, type inference. So type annotations, right? This kind of gets into static versus dynamic typing, right? So many languages require or at least allow type annotations on variables and functions, right? So think in Java we say something is a string or an int or a list or whatever, and we have to do that for every variable, right? We can't just create a new variable and not tell us what the type is. That's a type annotation. So the programmer uses them to supply static type information to the language system, right? This gives, like Java and other languages, the ability to infer what type, or actually to know exactly what type it is, so that you can statically check everything will match up correctly prior to it generating the compiled version of the program. Now, there are other forms. They also act as a form of documentation, make the programs easier to read for people, right? So that you can know, by just looking at the code, exactly what type is expected, and it can give you a better capability to reason by just looking at the code. But it's also part of the language. So part of the language is syntax for describing these types, right? In ML, we have the different type descriptor capabilities. For example, we can combine parameters using the star, and then the arrow operator to another type, right? And then we also have the concept of the list in ML. These all give us the way to construct different type annotations. Well, there are also concepts known as intrinsic types. Some languages use naming conventions to declare types of variables, right? For example, dialects of BASIC use the dollar, the S dollar as a type of string. Perl uses different markers to describe different types of variables. For example, if you put a hash before a variable name, that meant it was a dictionary. If you used an at symbol before, I think that was for an array. Dialects of Fortran use the capital I to denote an integer. So these are very similar to explicit annotations, and they supply static type information to the language system and also to the human reader. There's extreme type inference, right? So this is the opposite, right? The goal of systems that have type inference that are also statically typed, so they know the type information at compile time. The goal of these languages is to reduce the amount of type annotation, or boilerplate code, if you will. And this is like ML. In ML, it's often the case that we don't want to provide that type information if we don't have to. But you can, and it does make it much more readable. But ML will attempt to infer as much as possible using as little information as necessary. But it can infer a static type for every expression and for every function, and typically would require no annotations if it's done well. But there are other languages that use a more basic form of type inference, right? And almost all languages do this, including Java, which uses for oftentimes, for example, you have you have constants that, or we'll say literal values that have their own static types, right? So all numbers in Java are assumed to be an integer, but we can actually give a little bit extra information to reduce them, or to induce them to be a different value. For example, D means it's a double, F means it's a float, L means it's a long. If I put a 0x in front of it, then it actually means it is a hexadecimal value. So instead of 10, it's actually 16. So we have these different capabilities to understand what's going on by giving minor annotations or simple inference types. But normally, if we just saw 10, we'd assume an integer value of 10. So that's a form of inference. There are other forms of inference in Java, for example, on generics. On the right-hand side of an expression, I can, when I'm constructing a new generic type, I only have to use the diamond. I don't have to put anything inside of it because the system will infer that. Expressions also have static types, or may have static types, and they can be inferred from the operators and the types of the operands themselves. So For example, in Java, if a is a double, a times 0, we know that 0 is a double 0. Well, the overall value of this expression will be the value 0.0 as a double, because a was a double, even though 0 itself is actually an integer. Alright, so that gets us to the next level of type checking. So typically we have stack type checking, right? So in the most languages that we've used have some sort of stack type checking, including ML. And so stack type checking determines the type for everything. Every single part of the program will be the type will be known prior to ever running the program. So that means all variables, functions, expressions will be the type of those will be known. And if it cannot be determined, or if it doesn't match as expected, then that throws a compiling error, right? That leads us to compile time error messages when static types are not consistent. For example, operators, if I say 1 plus the string ABC will cause an error, right? Because there's no way to add ABC as a number to 1. On the other hand, if I flip that around, ABC plus 1 probably will work. We can also say we can't round the string ABC. That doesn't make any sense. And then we have if ABC then. Resolved to? ABC is a string. It's not some sort of Boolean value or something I can evaluate. Although, for example, in Ruby, right, we could evaluate that. Interestingly enough, most modern languages are statically typed, although there are languages like Ruby which are dynamically typed. I would say most, we'll say enterprise-grade languages that are used today are statically typed. Dynamic typing, on the other hand, in some languages, programs are not statically type checked before being run. Example, Ruby. A second example, JavaScript. Right? They're usually still dynamically type checked. At runtime, the language system checks that the operands are of suitable types for the operators. So you won't know there's an error until your program breaks. And so this is actually makes it an annoying process to go and debug your program, because you have to sit down and run it every single time, as opposed to being able to use the compiler to make that check for you. So these are arguments against dynamic typing. Interesting enough, typically people like dynamic typing because it's a faster turnaround time to actually build code. So you have an argument for and against this. I kind of like both ways of doing things. I like languages that have what appears to be dynamic typing, but it's really just strong type inference, and still catches things at compile time. Example, Lisp, right? The Lisp function that's shown here, we defining the function f, which takes the tuple or the list a, b in as parameters, and returns the addition of a plus b, right? It won't work if a or b is not a number, but you won't know that until it actually runs, right? You have to actually know that this is not going to work correctly. So if you run the program with an improper call like f, where it takes in nil, it's not going to be caught at compile time, mainly because there is no compiler. It will be caught at runtime because this is essentially dynamic typing. This is similar to Ruby, right? You won't know that there's a problem with your Ruby code until you actually run it and find out it failed. But interesting enough, it still uses types. Although dynamic typing does not type everything at compile time, it still uses types. For example, in Ruby, right? I'm going to go back to Ruby a lot about this. In Ruby, if we're writing code, we will not know the value of the variables. We know that we can infer the type by thinking about what is there, but in reality it won't actually know that type, and it uses this concept called duck typing, which is their notion for type inference as well as dynamic typing. But JavaScript also operates very similarly. You define a var, everything's defined as var as the type annotation, and then it essentially comes out that you can create it can be of whatever type, and you have to be the smart enough as a programmer to ensure that what you're doing will work, and that any types that you feed into a function or into a program will be what the actual code is expecting. Anyway, but going back to this, so we have dynamic typing. It does not type everything at compile time, but it still uses types. In a way, it uses them even more than static typing, right? Static typing just ensures at compile time everything is good to go, and then doesn't really worry about it at the end. On the other hand, dynamic typing, it needs to have types to check at runtime, right? We have to do the runtime type check, otherwise it won't work. So the language system must store all the type information in memory. So it actually makes it so that we can do really deep level inspection, and this is a technique known as reflection, which I believe we will talk about later on. And we may even go a little bit deep into this, but reflection is a very powerful technique to allow us to inspect what's going on with the program while it's running. And Java, C#, Ruby, most modern languages have some form of reflection capability built in. So static and dynamic typing, it's not really this. It's not. You don't find languages that have just static typing, or languages that just have dynamic typing. Typically, it's some gray in there. Statically typed languages often use some sort of dynamic typing. For example, when we were looking at object-oriented systems and their subtypes, right? That's a form of dynamic typing. Although we give it a type, and we have to infer that it is either, if it's an abstract type or an interface, we know that we can't expect those because those cannot be instantiated. So it must be one of their subtypes or their some descendant class of that one that can be used there. So it's a form of dynamic typing, but and oftentimes everything is typed at compile time, but compile time type may have subtypes. So that's what I was just talking about. So at runtime, it may be necessary to check a value's membership within that subtype hierarchy, right? So is it possible that it is one of these subtypes? This problem arises, as I said, in object-oriented systems, and we'll talk about that when we talk about those issues in Chapter 13. Dynamic typed languages often use some sort of static typing. Static typing can be inferred for parts of Lisp programs, using constant types and declarations, right? Lisp compilers can use static type information to generate better code, eliminating. So that's the interesting thing. Even though it may be dynamically typed when you write the code, the compiler itself can infer static type information in order to generate more efficient code, and also eliminate a lot of the underlying runtime checks, which cause the program to be slower during execution. Explicit runtime tests. Oftentimes, languages allow explicit runtime type checks. So, for instance, when you're working with so in Java, you have a type hierarchy, right? And you need to execute a method from a subtype, but you only have a variable holding the type of the abstract class. Well, the problem here is if you need some special underlying method from the subtype that's not available in the supertype, what we need to do is we run an instance of check. If it matches that subtype, then we can actually use that to then ensure a cast and then execute the method that we care about. And it's not probably the best way of doing it, but it can be done. Other languages allow this, so you can branch on object so you can use an object type in a switch statement to allow you then to execute conditional code based on type. Both of these things are considered to be code smells when we're talking about object-oriented design, but that's a thing I leave for the software engineering course. Hopefully you learned something about that. These require, it should be known that these require type information to be present at runtime, right? So this is actually instance of and type case. These are actually typically parts of the reflective capabilities of these types of languages, right? And so, and they appear in typically in more statically typed languages, right? In languages that are dynamically typed, we don't really worry too much about this. We let the underlying system handle that, and if it fails, it fails. Then the next part we get into is strong versus weak typing, right? The purpose of type checking is to prevent the application of operations to incorrect types of operands, right? So in languages like ML and Java, the type checking is thorough enough to guarantee this, right? So we can ensure in ML and Java that if we perform an operation on a type, it is applicable, and if it's not, it throws an error. In other languages where this is not necessarily guaranteed, we would call that weak typing. When we can guarantee, it's strong typing. But this gets into languages like C, right? There are holes in the type system that add flexibility, but weaken the guarantee, and that just gets us into weak type checking. C is not the best at this, given the way it's designed. Finally, we get to type equivalence issues. So we ask ourselves, when are two types the same, right? And that's always a question that's it's important for static and dynamic type checking, and it's important just when we're developing types themselves. So, for instance, a language might permit the assignment of B to A if B has this, or equivalence of A and B if B has the same type as A, right? Or we'll say assignment. So I can assign B to A if B has the same being in quotes there type as A. Different languages decide type equivalence in different ways. So there's different things that we can do. We can say name equivalence, which is where types are the same if and only if they have the exact same name. We have structural equivalence. We can say that two types are structurally equivalent if they are composed of the same primitive types using the same type constructors in the same order. That's something similar to what you see in ML, right? These are not the only two ways to decide equivalence. They're just the two easiest to explain. Languages often use some weird odd variation or combination. As we will see with almost every topic we consider here, languages use some not quite, they're always like a one-off or some mixture of things. So for example, type equivalence would be, if we looked at in ML, right, we create a type IR pair 1, IR pair 2. They're both int by real. And so if we create a function, right, where we have x and IR pair 1, and we look for the, it returns the first of the tuple, right, of x, we could actually we could pass in both IR pair 1 and IR pair 2. Name equivalence would not permit this, right, because they're not the same names, but structural equivalence would. And interestingly enough, ML would permit it, right, because it's looking at the underlying structural type, right? It doesn't care what the name is. It just cares that the type matches. On the other hand, if we were to look at I believe this is, you have some var counts. This is Pascal. We have counts 1 and counts 2. Both are the exact same thing, right? They're an array that is indexed from A to Z of type integer, right? So if we try to assign counts 1 to counts 2, name equivalence would not allow this because they're not the same name, and structural equivalence would permit it. But most Pascal systems don't, because they rely on name and not on structure. So the interesting thing in concluding of all this, right, a key question for type systems is how much of the representation is exposed, right? How deep can I get into the underlying memory issues and things like that? So we also know that some programmers prefer languages like C that expose many of the implementation details. They offer the power to cut through type abstraction, and when it is useful or efficient or fun to do so. On the other hand, other languages, others prefer languages like ML that hide all the implementation details through abstract typing. Some prefer something that's a little bit more of a mixture, like Java, which has some primitive types, but then also has higher level types. Typically, people who like ML or Haskell or the functional languages prefer this abstraction because it's much more mathematical. They like the abstract, if you will, the abstract type theory that kind of goes on with this, and how we construct these types and make them what they would consider to be sexier mathematics. But at the same time, I find that a lot of those arguments are flawed, not because they're bad, not because their ideas are bad, but because it's those who have gone to the great lengths to construct this actually make it far more difficult than it needs to be to understand it for the average developer. Finally, I want to go back just a couple slides to the strong versus weak typing. This is something very, very important to understand the difference of, and so we need to understand what the difference between strong typing and weak typing is. And so we need to understand that strong typing is, we have to look at this type checking, right? The whole understanding of this is to essentially prevent the application of any operation to types that it's not applicable to, right? So we take any operation, so it's operands. If we're talking about a method call, it would be the parameters and the assignment of the result. We want to make sure that it is impossible to assign the resulting value to a variable of the wrong type, or to take in values that are not applicable to the function. If we ensure that that can never happen, that's strong typing. That's ML, that's Java. If we allow it to be able to get past that, we can accidentally take in the wrong values, or we don't always make sure that that happens. That becomes weak typing. Okay, it does not. The type checking system does not ensure that the application of the operation does not prevent the application of the operation to incorrect types of operands or the assignment of the value to the wrong type. So just bear that in mind. That's the difference between strong and weak typing. I need to be sure that you all understand that. All right. So beyond that, we just need to realize that all these things are different issues that we need to consider whenever we're constructing or working with a language. Being able to understand the aspects of your language and why we pick these things. There are reasons to select them versus not select them. There are reasons we pick different languages for different jobs. These are all the whole point of what we're learning here, is that when you're working out in the field, you can sit down, and when you have to pick a language, you can say, well, you know why I want to use Go, you know why I want to use Rust, is because they're imperative, and they have strong typing, and they provide a type system that is fully formed, etc. Or here's the reason I want to use Haskell. I really like the mathematical notion behind it. It's going to solve the problems that we have. We have a lot of issues with working with types and type systems, so we need to develop this in the way that will work for us. So picking the right language for what you're trying to do. Oftentimes I know people who select languages like Python and Ruby with their dynamic typing because it allows them speed of prototyping. So that can be a very useful, especially early on in development. But maybe you want to shift to a stronger typed language when you start building much larger and larger programs. Being able to make these decisions and understand why you're going to make them is a key part of being an excellent software engineer. And understanding these languages and why these tools are used the way they are is what will make you a better programmer. Furthermore, when you're connecting this concept to both theory, right? So now we've talked about the underlying mathematical notations of how we build these type systems up. That brings us back to comp theory, discrete mathematics. We understand why we had to learn those classes in order to be able to even be here. But at the same time, we can now start to see how are we going to apply this when it comes to building a compiler. Why is it that we may or may not want to use union-based types? Maybe you want to design your own language in the future. Why should you or shouldn't you not use union or intersection-based systems for creating types? Thinking about all these things and all these problems is the first step in really understanding this. And bear in mind that this is one of the main components of computer science and in our entire discipline. So anyway, I'll leave you with that thought for the day. Have a great day and enjoy. I'll see you in class.